Hello, my name's Kevin. Today I'd like to show you what 40 years of circuit breaker, intimate knowledge of circuit breaker is in critiquing a panel that I found on the internet. So what we have here is a panel looking at the particular products there. I can see that these appear to be Mitsubishi products, somewhere in the region of 600 to 800 amps here, and 250 amp products as a mid feed going out this side. Some are not connected on the load side, which would probably indicate that these were there as spares, and some are connected to bus bars which have tap-offs of smaller wire, indicating possibly the use of small clip-in type products downstream. So firstly, if we have a look, it looks fairly neat. It's coming in on the top here, going out on the bottom. So it's what I call normal feed, not reverse fed. It's connected to bus bars, connected and switched around and supplied to the top. On some of them, they do have wires connected, and some have bus bars connecting. Possibly these are higher ratings than those. The bus bars themselves are plated, so they look pretty attractive from that avenue. We've got CTs connected on the load side. So for a product in the 600 amp class, we can possibly anticipate something between 20 and 30 Ka as the short circuit. The lead through into these busbar areas will be in the region of 12 to 15 Ka. And as such, these bus bars would have to carry the current that it would have here. It has to deal with the voltage, so they've got to have independence from each other and not allowed to be connected closely. They've got to deal with the mechanical forces of possibly 15 Ka here, and that's, of course, the problem area that we're going to have some discussion on, because this type of panel appears to be handmade. It's not something that you would buy from a manufacturer as a sort of a standardized kit. Immediately we look here and we see that there are no interface barriers fitted at any level. So on the main breaker or the sub ones, these breakers do come with at least two. Products that have none supplied by the manufacturer could be connected without any. In this case, there will be provided from the manufacturer. And we can see here that without that interface barrier, there is a risk of a short circuit occurring after a large short circuit trip on the breaker itself. So ionized gases come out the top of these particular products. And if you don't have those barriers fitted, you will end up with a secondary calamity between the phases, which will result in a short circuit external to the breaker, resulting in a lot of damage. So the withstand on here, you can also see that there's no insulation on these. So while they look good and attractive, they could very easily result in something dropping down from the top here, a piece of wire from manufacturing of this type of thing, or a spanner or something falling through the panel will also create a short circuit here, an immediate short circuit, I should say. And so without any interface barriers, there's a risk that these would immediately have a short circuit external. Of course, that will damage the product completely, requiring replacement of the circuit breaker that is involved in that. We can also see that we go red, white, blue, red, white, blue, red, yellow, blue, red, white, blue, red, white, blue. And breakers that are put together, completely together, where there's no gapping in between, will require a barrier fitted in that zone as well. Or the alternative to this would be maybe red, white, blue, red, white, blue, blue, white, red going through here. So we could have a look at that as an option to having the interface barriers. As I said, these are 250 amp breakers here, and we can see a bus bar connected here, which would be in line possibly with 250 amps here. And then we've got a wire one connected here, bolted through. Now, this is where the risk could also be. This range would be a 150 to 250 amp product. And so these cables here would be problematic. If there were, let's say, 100 amp breakers here, and these cables were selected for 100 amps, we might have an alternative problem. So when we look at this sort of product that we've got connected in here, this interface between the main upstream breaker and then smaller downstream breakers becomes quite critical, especially when the large breaker is much larger than the breakers downstream. I'll show you on the load side where there's definitely a problem on this one. So let's have a look here. We've got a 600 amp breaker. It provides all the protection all the way up to this level down here, up to this zone down here. And so if you suddenly used very small cables, let's say, for instance, there was some 250 amps and then 100 amp feed out of here, and you used a 100 amp cable here, you might find that the cable itself cannot withstand 10 Ka or 20 Ka of the main protection here, and so would be at risk. Mechanically and electrically could be a problem going forward. We can also see with this sort of approach here is that there's absolutely zero compartmentalizing. So even if this product as the main had a huge flash on it on the top, it would probably continue right into this zone as well and destroy the whole panel. Or a breaker tripping in on the load side here and causing a flash in the top. There's going to be dynamic stresses with interface forces here, and the arc could be forced to travel up or down this bus bar until it reaches the end and flashes over to ground. So compartmentalizing is important if you want to sustain the short circuit and trip zoned energy within a specific area. So if there was a secondary type of problem, it doesn't develop elsewhere through your panel. This type of panel is going to last to have a major short circuit and be a short circuit. It'll be the death of the panel. It'll be fatal to the whole panel. It'll self-destruct and require a whole panel. And this is where the type testing is such an issue when it comes into having circuit breaker panels pre-tested. One, they are checked for short circuit viability. They are checked for compartmentalizing. They are actively tested before you have a short in your warehouse or your factory, before there's an issue. So let's have a look again on the load side of the breakers. Here we can see a long stem bus bar, 3 connected there, red, white, blue. And from each one steps a cable and goes out to a small, presume a small breaker somewhere in another panel, or maybe on the left or right of this particular panel. Now, when we have a look at that, of course, we said we had potential maybe 20 Ka here. All these products here provide protection all the way downstream to those small products. And if we've got very low currents here, this breaker, say, has a 250 versus a 20 amp supply, maybe a lighting plug circuit, and you're going to have cables going down here at 20 amps. Again, these cables may not be protected fully by the upstream breaker. They might be, I mean, a 250 amp breaker is not going to trip at 250 amps. This cable going to a 20 amp breaker could be legally anything from 2.5 to possibly 6 millimeters squared. And 6 millimeters squared is not going to take 250 amps before, or let's say above 250 amp plus 35% when this breaker trips. So that cable is going to get super hot. It's going to get damaged. It can fuse off. So ideally, all the product on the load side of here should be rated to this breaker here, as this one, if it was a 600, would cause all the bus bars here to be 600 amp feeds out, fully rated at this breaker's rating. And as these, if they were 250 amp, would have to be bus bars like that going out to the load or going out to a large cable connected. When you multi-feed these out to small loads like this, These little cables, one, are not protected by this breaker upstream, and only on extreme capability will this breaker, in fact, trip, possibly protecting them in a way, but it will probably be fatal by the time this breaker trips. These cables will be melted and damaged. So this becomes a very important thing to look at this interface zone. And it's not just a matter of putting power on and getting power out and thinking, well, everything is hunky-dory in between. It's very important to look at the panel as an extension of the breaker's protection area as well. It's not just the loading of these cables. And this is the vital point that's carried through in type-tested panels, because this whole panel would have been pre-tested to a norm and has to pass, whereas this one, we're not sure what's going to happen. Certainly without interface barriers, I can tell you right now from my experience, anything on this side will probably destroy this completely there. It will probably destroy all the buzz bars back to there. This one here would destroy the main breaker, and if the energy shot through on this side might in fact start second and third level damage areas within the panel. Not something you want to do. The alternative is, of course, that everything has to be rated for that, rated from the KA level, which is very difficult if you've never tested your panel and you're just going to wire one to be effective from a load point of view. What we could have on here as another area of concern was if this was a 525 volt panel and we had a control voltage here, and we dropped droppers down from the bus bars to the control transformer, and we had 10 amps required on that control transformer. The cables that are connected from the bus bar to the transformer in this zone have to be protected, one, from the KA, and two, from the mechanical stresses to that cable. So there's no ways you could drop a piece of cable down here to a fuse set down the bottom and then go into the transformer. I am aware that you do get busbar connected fuses, which are pretty good in the sense of they are protected from their load side going down, and so they are permanently connected to the busbar. That is a solid connection. There's no requirement for loading and mechanical stresses up to the actual fuse itself. So those would effectively work. You would still possibly have to look at making sure that the fuse line down here is supported in such a way that mechanically any short circuit doesn't pull those cables apart and create a problem. As I said, a floating piece of cable within a busbar zone is really where a problem could develop quite specifically. So from a critique point of view, just a quick recap on this. Busbars, and that should have been tested. If you haven't tested them, you haven't got a type tested panel. By law and strictly speaking, anything above 10 Ka should in fact be a type tested panel. Any extension on a system like that should be done in terms of that same thing, not just an add-on of any panel. Interface barriers, very, 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 and I can't say too many, very important to be fitted, and fitted soundly up to the back metal plates. If you've got metal plates at the back, I'm not quite sure what's in here. Very important to have that type of thing. You might even find that some people put a toughnell or an insulation plate below the breaker between the panel and that, so that you enhance the Ka area, so there's no conductive material in the zone. That's another thing. If we look here, these buzz bars are basically extreme. Well, the side one is extremely close to the breaker. It's probably within the area where the manufacturer says, I want 15 millimeters or 20 millimeters till any metal part. And if you look at this buzz bar running through here, it's probably in contravention. I don't know what it is offhand, but it's not great to be so close. It should have been, the buzz bars look further apart from each other than they do to the breaker, but the breaker is going to have a gas out here. So if you are a manufacturer, please look out for that type of thing. If you are doing mods to panels, something to contend with as you go down the line, and to look a little bit more in depth than pure, what breaker do I put there from a current, even a Ka perspective. from a manufacturing perspective, because you could easily have a problem there down the line. All right, and so if you have a query, come back to us on this one. If you like these videos that I post on here, think about liking them and passing them on to your mates. Let's have a look at them and see if we can get the industry up to a point where the industry gets better and the risks are less.